All right, let's take a look at our second video from section 1.2 where we're going to be analyzing functions. This video is going to talk about how we look at a graph for increasing, decreasing, or constant, as well as mins and maxes and what it means to be bounded and what symmetry means for a function. So increasing and decreasing, so we read a graph like we read a book. We read it from left to right. So if your graph is increasing or going up from left to right, again, start on the left and then just put your pencil on. If you would have a hiker here and the hiker is going up, that's considered increasing. From left to right, if you are going down, that would be decreasing. And if you aren't going up or down, that would be considered constant. Okay, so, and it could be on any interval. So we're going to see that it doesn't have to be fully increasing or fully decreasing. It can have different intervals at which it's increasing and decreasing. So we take a look at this. Again, we talked in the last video about interval notation with the hard brackets being equal to, soft brackets being not equal to. So let's take a look. You can hopefully see that there's kind of three changes here of this graph. So we've got this chunk that's decreasing, right? So we've got a decreasing portion, we've got a constant portion, and then we've got an increasing portion. So again, remember, you're reading this left to right. So start on the left-hand side and just go. So if we name the decreasing level, now you do this for the x values, okay, because we're reading left to right. That's an x movement, and then we're telling what the y's are doing. The y's are decreasing on this x interval, or the y's are staying constant on this x interval. So increasing, decreasing, constant are always x intervals. So for this case, let's just say that this graph had an arrow here, okay? It's going all the way over here. So it's decreasing from, what's the value way down here? Negative infinity, okay? With soft brackets here, negative infinity up to -2 is where it changes. Now at -2, it's not doing anything, okay? So you can't be increasing or decreasing at just one point. It has to be on an interval. So we're gonna use soft brackets for this because it's not actually part of the decreasing. Okay, so soft brackets on this whole thing. Then the constant interval happens between here. So happens from here to here was the constant. So our function is constant from x equals -2 all the way to 2. And then it starts increasing at x equals 2 up to this number, infinity. Okay, so you could have multiple decreasing levels or multiple increasing levels. Oftentimes we won't have constant levels. Okay, a lot of the functions that we analyze don't have a constant portion. So you'll just write down which ones you see. So let's take a look at this next one. Okay, so this one here, if we're reading left to right, this part right here is increasing. Okay, then it stops. Okay, at this x value of -1, and it starts over down here, and it's still increasing up to this local maximum here. Okay, so it's still increasing on this interval. But when we write this out, we actually have to make a break here because this domain doesn't exist. There's nothing happening at -1. So when we write this, okay, again, this low value down here, so we're increasing from negative infinity to this point, which is -1. Then we start over, so remember you put a u there, at -1 up until this x value. Okay, so this x value is -1. What's this x value? Well, that's 0. So then it's increasing from -1 to 0. Then it starts decreasing from 0 to what's this value? 1. So now we're decreasing from 0 to 1. Again, you're naming only x values. And then decreasing is what the y's are doing. Then right here, decreases again from 1 to infinity. Okay, soft brackets on all of that, but you're splitting up these x values. You're only naming x values. And you should pretty much have all of them covered. unless there's some big split horizontally in the graph. All right, and I said I would talk about this where if there's a lower boundary or an upper boundary, this is called boundedness. Okay, and it just means if there's a boundary, if there's a spot that the graph either doesn't go below or doesn't go above. So if there's a spot that the graph doesn't go below, there's a low spot where the graph stops and there's no graph below it, that's bounded below. That means it has a lower boundary that it can't go past. If that boundary is above it, okay, where there's no graph above that line, then that's said to be bounded above. There's an upper boundedness or an upper boundary. Okay, if there's a boundary above it and below it, so there's a spot where there's no graph above and there's no graph below, that's considered bounded. It has an upper and a lower boundary. So we've got three things. It could be unbounded, so we have four things. It could be unbounded, there's no boundary. Think linear or cubic, okay? It goes up and down. So you could have unbounded, you can have bounded below where there's a lower boundary, bounded above where there's an upper boundary, or bounded. If you say bounded, that means it's bounded above and below, okay? It can't go up to infinity or down to negative infinity. So if we take a look, okay, this quadratic right here is bounded below. There's a lower limit that it can't go past. So this one is bounded below. Okay, this one has an arrow up and it has an arrow down, meaning no local mins or maxes. So this one is unbounded. This one just keeps going from this high point to this low point, back to this high point, low point, high point, low point. So it has an upper boundary it can't cross and it has a lower boundary it can't cross. So it is both bounded above and below. So we would say bounded. So you don't need to write out bounded above and below, just write bounded. So if there's a local min or a local max, that's where you end up with boundedness. Okay, so you know what a min or a max looks like. It's where it switches from increasing to decreasing. So if you have in this case, we have a decreasing side of the function and then it goes to increasing. So where it switches from increasing to decreasing, that's either a min or a max. So decreasing to increasing is a local min, increasing to decreasing is a local max. And so you've got here, this is the absolute min of this function. There's nothing that can go lower than it. Okay, so there's no graph below it, where this one is considered a local minimum because there are smaller values than it, but it does switch from increasing to decreasing right there. So if we were going to name these, so if we're going to name these mins and maxes, okay, so let's name the local max. Okay, so if I asked for the maximum point or the local maximum point, you would actually name the ordered pair 0.456, comma 1.324. And then if I asked for the max value, okay, there isn't a max value in this case because this function goes up to infinity. Okay, and then if I asked for the local mins, the mins or the local mins, you would name them. So you would put the point negative 2.057, comma negative 24.057, and 1.601, negative 1.766 for this one. And then if I asked you for the minimum value, okay, that's the actual y value, the smallest y value possible on this graph, which is just that y value. So the minimum value is negative 24.057. So minimum point, name the ordered pair. Minimum value is the y value, just the y value. So now, again, those mins and maxes, those local mins and maxes is where you're increasing and decreasing switches. Okay, so we're going to actually analyze this on this next slide. So when we're taking a look here, we've got, this is the same exact graph, I just widened it. So let's take a look here. So the function name here again is quartic, like we talked about on the previous video, and that's an x to the fourth. So if we're doing bounded, this one has arrows going up, Okay, but it has a minimum value. It has a low point. That means it's bounded below. Okay, and we'll say what the lower boundary is. The lower boundary is negative 24.057 because that's the lowest value. So this is the line that this function will not go below. All right, let's take a look at increasing, decreasing, and constant intervals of this. Okay, so increasing, decreasing, constant. So here we're decreasing until this x value. Okay, so I like to label these up on this x-axis. Okay, so this was negative 2.057. That's the x that it switches. So we started down here at negative infinity up until here. This is our decreasing level. Okay, then we switched over and now we start increasing from here until the next maximum. So when this switches, so the x value here is 0.456. That's where my next switch in increasing to decreasing happens. So from here to here, we were increasing. So this interval right here is an increasing interval. Then we switch and start decreasing until the minimum. Okay, so that x value there is 1.601. And we were decreasing in that interval. Then we start increasing again for the rest of time. Okay, so all the way for the rest of the graph up to infinity. So from here to here, we were increasing. Now you need to just name those intervals. Okay, so again, decreasing for this interval. So we were decreasing from negative infinity to negative 2.057. And then we were decreasing on this interval as well. So 0.456 up to 1.601. So those were the two intervals of this graph that we were decreasing. Then we were increasing from here to here. Okay, so we were increasing from negative 2.057 up to 0.456. And then again from 1.601 to infinity. So again from here to here. All right, then the last thing that I want to talk about is symmetry and what symmetry looks like on a graph. So there's two types of symmetry, even or odd symmetry, that we're going to be worried about. And we'll get into some of the algebraic stuff later. But symmetry, if a function has even symmetry, then it's going to be symmetric with respect to the y-axis. So just here, it has to fold over the y-axis. It can't be moved off the y-axis. Okay, so it's not the degree of the function because all quadratics have vertical symmetry. But if it's over here, this one's line of symmetry is here. It's not the y-axis. So it has to be the y-axis for the function itself to be considered even. So it's not the degree. It's not the same as the degree of the function. Okay, when you graph it, it has to be symmetric about the y-axis. What that looks like in a table is that the positive and negative version of an input give you the same exact output. So when you plug in -3 and +3, it gives you the same y value. -2 and 2, -7 and 7, a number and its opposite give you the same output. Okay, so when you plug in the opposite of a number and the number, they equal. So in a table, it looks like this. Algebraically, when you actually plug in 3 into the function and -3 into the function, that output is the same. That's even symmetry. Odd symmetry is symmetric with respect to the origin. That means it's a 180-degree rotation. So if I took this chunk and rotated it 180 degrees, it would land back on itself. So if I just took this and rotated it 180 degrees, it would land back on itself. So graphically, it has to go through the origin, and then either the first and third need to be the same or the second and fourth quadrants need to look the same for it to rotate over onto itself. In a table, what this looks like is a number and its opposite, so 3 and -3 give you opposite outputs. So 3 gave me 27, so the opposite of 3 gave me the opposite of 27. 2 gave me 8, so the opposite of 2 gives me the opposite of 8. So plugging in an opposite gives you back the opposite of the function. Okay, so whatever I plug in gives me back the opposite. So if I plugged in -7 and it gave me back 10, then when I plug in 7, it better give me back -10. So a number and its opposite give you back opposites. So if we go back to this function and take a look at symmetry, yes, this one goes through the origin here, okay, but it doesn't rotate back on itself because this maximum doesn't show up over here. Okay, so when I rotate this back, and their end value, their end behavior is both going up, so it couldn't rotate back on itself. So this one has none, because again, it's not symmetric over the y. You can't fold it over itself, and it can't rotate, so there's no symmetry in this one.